Hello and welcome to the worked example video for 7.1, and here we're going to be doing some more examples of proving or verifying these trigonometric identities by using our fundamental trigonometric identities. So let's take a look at some of these examples. So first, verify that 1 minus cosine alpha over sine alpha is equal to sine alpha over 1 plus cosine alpha. So we can start with either side. I'm going to go ahead and start with the left-hand side. 1 minus cosine alpha over sine alpha. Okay. Now there's no cancellation here. There's no real identities that we can use right now because we don't have any cosine squareds or sine squareds or anything like that. So now we need to go down to that third hint step from the last video, and that is creative multiplication by 1. In other words, I want to multiply this by something that's equal to 1 that's going to help me to get over here. Now we have a couple of clues. First, we know that I have a 1 minus cosine alpha on the top, so I have a conjugate expression that I can multiply by. Remember, with our a minus b times a plus b, those conjugate expressions, when we have this form, if we multiply by its conjugate, we're going to get something that we can apply the Pythagorean identity to. Okay, so the conjugate expression of 1 minus cosine alpha is just 1 plus cosine alpha. Now, even not having that information about conjugate expressions in mind, we could infer from our right-hand side, we know that I have a denominator of 1 plus cosine alpha. So if I introduce the denominator of 1 plus cosine alpha here, we should be able to get over there as well. So either way that you reason it out, multiplying the top and the bottom here by 1 plus cosine of alpha should help us to get somewhere here. And really, keep in mind, I'm just multiplying by 1. Whatever we multiply by, it always needs to be equal to 1, and we have no problem here with that. So here on the top, I have 1 minus cosine alpha times 1 plus cosine alpha, so we know that that equals 1 minus cosine squared alpha. Or in other words, 1 squared minus cosine squared alpha with our a squared minus b squared identity. And on the bottom here, for now I just have sine alpha times 1 plus cosine alpha. Alright, now we have this expression on the top. Like I said before, we know we can use our Pythagorean identity here once we multiply these conjugates together. 1 minus cosine squared alpha by our first Pythagorean identity is equal to sine squared alpha. This is all over sine alpha times 1 plus cosine alpha. Now we see we have a cancellation. This top becomes just sine instead of sine squared. It cancels with the sine on the bottom, and we get sine of alpha over 1 plus cosine alpha. We see that creative multiplication by 1 can come in quite handy. This problem turns out to not be too bad once we figure out what we need to multiply by. Alright, now let's take a look at another one, and I'm going to talk about a different method that we can use. Not really a different method, but kind of an alteration of the method we've been using that can sometimes be helpful when we get stuck. So we want to verify that tangent x plus cotangent x all squared is equal to secant squared x plus cosecant squared x. So let's go ahead and start with our left-hand side. I have tangent x plus cotangent x all squared. Now I could write this in terms of sine and cosine, but it's not very apparent that that's going to be helpful here. So first, why don't we go ahead and expand this out. This becomes tangent squared x plus 2 tangent x cotangent x plus cotangent squared x. Okay, let's try to simplify a little bit more. Let's leave this tangent squared x alone for now. I have 2 tangent x cotangent x. Now take a minute to think about what tangent x times cotangent x equals. Tangent is sine over cosine, cotangent is cosine over sine, or perhaps an easier way to think about it is we know cotangent is 1 over tangent. In any case, tangent times cotangent is always just equal to 1. So this is just 2 times 1 plus cotangent squared x. Now I mentioned we're going to talk about a new method. Let's just say, even if you can see what the next step is, even if you can move ahead here, just for the sake of introducing this technique, let's just say that we got to this point and we got stuck. We can't see what to do. We don't know what to do here. Well, something that we can do is we can work with these sides independently of each other, right? We know from the first video that it's important not to set the two sides equal to each other, but I can start from either side independently and try to meet in the middle. So let's see how that works. Let's just say I get stuck. So I'm going to say, well, I'm going to start from my right-hand side and see if I can get my right-hand side to look like one of these middle steps. So I have secant squared x plus cosecant squared x. And all these squares, they just scream Pythagorean identities, don't they? So secant squared x, I know this is the same as 1 plus tangent squared x. I'm going to write it as tangent squared x plus 1. And I know that cosecant squared x is 1 plus cotangent squared x. So really, adding those ones together, I get tangent squared x plus 2 plus cotangent squared x, don't I? And we see these two are equal to each other. So we started from both sides independently, but look now, we have a chain. From left-hand side, we get to here, we come over to here, down to here, which is actually the same thing, to here, and we get to the right-hand side, right? So the arrow, just kind of going around this way, comes back. And in reality, even though we worked with both sides independently, we still have a left-hand side equals right-hand side chain of equalities where we never had to set our original two statements equal to each other to solve the problem. So this is very much an acceptable way to prove this identity. Okay, if you ever get stuck, if you start from one side and you get stuck, no problem. Go ahead and start from the other side and see if you can get the other side to match one of your steps that you have so far from the first side. Okay, then you can just kind of link them all together and you end up with that chain that we're looking for. Left-hand side equals right-hand side. Okay, no problem there. Now there's one other type of problem we sometimes see in this section, and that deals with trig substitution. This problem says simplify the expression as a trigonometric expression with the given substitution. Okay, so we have this expression, x over the square root of 1 minus x squared, and we're asked to use the substitution x equals sine theta. Now this is very useful in calculus 2. There's a group of integrals that look something like this that are very easily solvable if you make the proper trig substitution. And really the key is, every time we're making this trig substitution, what we're trying to do is we're trying to get a Pythagorean identity under the square root. If I get a Pythagorean identity under here, I can turn it into just a pure square and cancel out the square root. Okay, so let's see that in action. Here I have x over the square root of 1 minus x squared. Making the substitution that they give me, this x on top becomes sine theta. And on bottom, we get the square root of 1 minus sine squared theta. Now one of the important things for these substitutions that we won't really get into here, but just kind of a little preview hint towards calculus, it's very important here, this square root is only going to be a real number if the entire sum or difference underneath it is between 0 and 1. Right? It can include, sorry, if this x squared is between 0 and 1. I should say if this entire quantity underneath is positive or 0. Now in this case, that's only going to happen if x squared is between 0 and 1. Now we can include 0 here, but we cannot include 1 because I'd get 1 minus 1 and I'd be dividing by 0 and this would be undefined. But really I need to have x squared greater than or equal to 0, greater than 1. Well, that means that x itself is strictly between the values -1 and 1. These are the only values for x that I can square and get something within this range here, right? Anything more negative than -1 or more positive than 1 is going to give me a larger squared value than 1, and I'll have that this is either a square root of a negative number or a square root of 0. So this trig substitution makes a lot of sense because I know that sine theta for all values of theta is going to range over the same possible values of x. In other words, the domain of this expression in x is the same as the range of sine theta over here. So we have no problem with this substitution. Now, as I mentioned before, the goal of the substitution is to set up a Pythagorean identity under the root, and we see that we do have one. I have the square root of 1 minus sine squared theta. From my Pythagorean identities, 1 minus sine squared is just cosine squared theta. So we get a cancellation in the square root and the square, and this is sine theta over cosine theta. And we can simplify this a little bit more. This is just tangent theta. So great. Now I'm going to continue on a little bit. This is the end of this problem. If you're asked this problem, our solution is tangent of theta. But just kind of a hint of things to come, let's just say I just started with this substitution x equals sine theta. Now if x equals sine theta, I could draw a triangle. Sine theta is x, so that means it's x over 1, so my opposite is x, my adjacent is 1, and by Pythagorean theorem, this side over here is the square root of 1 squared minus x squared. So just by my triangle, if we were going in the other direction, I would get that tangent of theta is equal to my opposite over my adjacent, which is x over the square root of 1 minus x squared. Now this is going to become useful in the next set of videos where we need to evaluate some of these mixed trig expressions in terms of x. Just keep in mind, if you have this kind of substitution, this relationship between a trig function of an angle and some variable, we can set up a triangle to solve for any of the other trig functions in terms of those variables. Alright, so in the next video we're going to start on a new section and we're going to be introducing some new trigonometric identities that we can use to solve these types of problems. We'll see you there.